Welcome to the Deep Dive. Today, we're tracing the really extraordinary path of a scientific breakthrough, one that utterly transformed our digital lives.
That's right. We're talking about a discovery that didn't just bag a Nobel Prize, but also boosted your hard drive storage capacity.
By an incredible factor of 100. It's kind of mind-blowing when you think about it. So, our deep dive today, we're going to distill the key insights from Peter Grünberg's own Nobel lecture. We want to give you a concise but comprehensive picture of how magnetism was fundamentally re-engineered. We'll follow his journey, starting from these quite subtle light-scattering experiments, all the way to this phenomenon called Giant Magnetoresistance, or GMR.
Yeah.
And our mission really is to pull out the most important bits of knowledge, make sure you're well-informed on this, remarkable piece of scientific history.
What's truly captivating here, I think, is seeing how something seemingly abstract, like observing tiny ripples in magnetic orientation.
Yeah.
These spin waves, how that could actually lay the foundation for such immense tangible applications. It really speaks to the value of, pure scientific curiosity.
Absolutely, even when the practical payoff isn't immediately obvious, right?
Exactly.
So get ready. We're going to peek under the hood of your hard drive, understand the physics behind why these discoveries were indeed so giant. Okay, let's set the scene then. It's 1972. We're at the Institute for Magnetism in Jülich, Germany. Peter Grünberg is there, immersed in the world of magnetic materials like europium oxide, europium sulfide, and he's fascinated by these propagating ripples, these spin waves. What was the puzzle he was trying to solve?
Well, his main focus was really understanding these spin waves in detail. And to do that precisely, he used a technique called Brillouin white scattering. BLS.
BLS. Okay.
Think of it like a supersensitive light analyzer. It uses this specialized optical instrument, a Fabry-Perot interferometer, to spot incredibly tiny shifts in the frequency of scattered light. And these shifts, they act like a unique fingerprint, you see. They're characteristic of the spin waves rippling through the material.
So he was looking for the expected ones first, the bulk spin waves.
That's right. They showed up as, predictable peaks in his data. But then came one of those classic science moments. Serendipity struck.
Ah, the best kind.
Yeah. A system breakdown, a repair, and someone accidentally mixed up the magnet leads during an experiment on europium oxide.
Oh, dear. Or maybe, oh, good.
Well, exactly. Because suddenly he saw something entirely new in the data.
Which led to the big question.
Yes. Why were these new peaks showing up on the completely opposite side of the light spectrum?
Okay.
They quickly figured it out. They weren't seeing the usual bulk spin waves. They were seeing the long-theorized Damon Eshbach surface spin waves, DE modes.
Surface waves, what made them different?
What made them so special was their unidirectional propagation, meaning they only traveled in one direction along the material's surface. And if you flip the magnetic field, poof, they reversed their travel direction.
Wow. So a simple wiring mistake. It accidentally revealed this deep fundamental symmetry in nature.
Pretty much. It showed how magnetic fields behave under time reversal. It was actually so significant, the finding later made its way into solid-state physics textbooks.
Incredible. Like the universe just whispered a secret because someone plugged something in wrong.
It's exactly that kind of moment. An unexpected result, even from an accident, becomes pivotal. It wasn't just, a curious anomaly.
Right.
It really confirmed these theoretical predictions about Damon Eshbach modes in a whole new way, using light, which hadn't really been done like that before for these modes.
And then as they continued, the thickness of the film started to matter a lot, didn't it? What happened when they used much thinner materials, like 200 angstroms of iron?
Yeah, that's a critical point. In those really thin films, the bulk modes, they actually split. They became a series of distinct standing modes.
Like guitar strings.
Kinda, yeah.
Yeah.
Like harmonics.
Yeah.
And the Damon Eshbach mode, the surface one. It suddenly appeared on both surfaces.
Ah, so it wasn't unidirectional anymore in those thin films.
Exactly. You could observe both propagation directions. It showed that just by changing the film thickness, you got this new level of control over the magnetic behavior.
Okay, so with that understanding of single films nailed down, the next obvious step was putting two layers together.
Precisely. What happens when you bring two magnetic layers really close, but separate them with a non-magnetic spacer?
Right, the tri-layer structure.
Yes. And that's where we enter this really intriguing realm of magnetic double layers. The DE waves on each surface, remember, there are 4 surfaces now, 2 per layer, they start to interact.
Go through their magnetic fields.
Through their oscillating stray fields, yeah. It's like they're magnetically whispering to each other across that spacer. And this interaction leads to entirely new, complex, coupled modes.
The Nobel lecture has these great diagrams illustrating this magnetic dance, as you called it. It shows how things change depending on whether the layers are aligned parallel or anti-parallel.
That's right. If the magnetizations are parallel, the frequency graph is nice and symmetric. But align them anti-parallel, and suddenly it's asymmetric.
Can you give us a feel for these modes? Like, what's a uniform mode versus an optic mode?
Okay, imagine the tiny magnetic moments in the layers, like little spinning tops or gyroscopes.
Got it.
In the uniform mode, all these tops precess. They wobble perfectly in sync across both layers, like a synchronized swimming team. That's the upper branches on the graph.
Okay.
But in the optic mode, the lower branches, they precess 180 degrees out of phase. So as one layer's magnetism points one way, the other points the opposite way during the wobble. It's like a magnetic tug-of-war.
Ah, okay, out of phase. That makes sense. So observing these coupled modes then became a tool, a way to understand this interlayer exchange coupling, or IEC.
Exactly. IEC is basically the magnetic conversation happening between the layers through that non-magnetic spacer. And we can predict how it should affect those modes. If the coupling is ferromagnetic favoring parallel alignment, it should increase the optic mode's frequency, strengthens the restoring force.
Makes it harder to go out of phase.
Right. But if it's antiferromagnetic favoring antiparallel alignment, it should decrease that frequency, weaken the effect of an external field trying to align them. So BLS let them effectively listen in on this magnetic conversation.
So the challenge became finding real antiferromagnetic, or AF, coupling, not just something caused by, say, rough surfaces.
Yes. Earlier hints of ferromagnetic coupling often turned out to be artifacts. Pinholes, orange peel, roughness, things like that. They needed a material system that would genuinely mediate this subtle AF coupling.
And that search led them to?
Chromium.
Why chromium?
Well, chromium itself is an antiferromagnet. And theory predicted that coupling through thin CR layers should oscillate and go back and forth between ferromagnetic and antiferromagnetic.
Yes.
Yeah, with a very precise period, just 2 atomic monolayers of chromium thickness. Plus, crucially, chromium was a good crystallographic match for iron. That was essential for growing the high-quality Vecrafé layers needed.
Okay, picture this. Mid-1980s, Grünberg's on sabbatical at Argonne National Labs. He's working with a team that's brilliant at making these perfect Vecrafé samples. And then the moment of discovery, the eureka moment.
And it really was a eureka moment. They compared their standard Vecrafé samples' gold interlayers, which showed clear ferromagnetic coupling with the new Vecrafé structures, and the BLS spectrum. Dramatically different. The optic mode's frequency just plummeted.
Ah, the sign of.
The unmistakable signature of robust antiferromagnetic IEC. Finally. It was, as he put it, sensational they'd found it.
But they needed to be absolutely sure, right? So they also used another technique, MOKE.
Right, the magneto-optic Kerr effect. MOK gives you a measure roughly proportional to the overall magnetization, and AF-coupled samples showed this distinctive shearing shape in the MOK curves as the field swept.
But shearing alone isn't definitive proof of AF coupling.
Exactly. Other things can cause shearing. This is where the BLS data was absolutely critical. The advanced BLS measurements provided that definitive first observation. It confirmed that the shearing seen in the simpler MOK curves really was due to antiferromagnetic alignment.
It highlights the importance of using the right tool for the job, especially for the initial breakthrough.
Absolutely. You need the sophisticated tool for the first unambiguous proof, then maybe use simpler methods for more extensive studies.
Now, their first studies confirmed AF coupling, but that predicted oscillation, the 2 monolayer period. That wasn't immediately obvious.
Now, looking at the lab notes from May '85, it wasn't clear yet. It actually took years of improving the sample growth techniques, getting those layers incredibly smooth and perfect to finally observe that theoretically predicted oscillation.
Wow. It just shows the complexity, doesn't it?
It really does. These systems are incredibly sensitive.
Okay, so discovering this robust intrinsic AF coupling that flung open a massive new door, it connected directly to Sir Neville Mott's 2-current model. How did that connection happen?
Well, Mott's model, which dates back much earlier, is quite elegant. It suggests that in magnetic materials, electrons behave differently depending on their spin relative to the local magnetization.
Spin up versus spin down.
Essentially, yes. Electrons whose spins are aligned parallel to the magnetization scatter differently than electrons whose spins are anti-parallel. And since spin flips are rare, you can basically think of two separate currents flowing in parallel, a spin-up current and a spin-down current.
Okay, two channels.
Two channels, each
Yeah.
experiencing different resistance.
And here's where the genius for applications comes in, right? If you could switch the magnetic layers between parallel and anti-parallel.
Yes, and crucially, do it within the electron's mean free path, the average distance it travels before scattering, which is maybe 10 nanometers or so.
Which was possible with those ultra-thin nanometer scale interlayers they were making?
Exactly. Those AF-coupled structures were perfect. The idea was, if you switch from parallel to anti-parallel alignment, you should see a big change in the overall electrical resistance.
How so?
Well, think about it. In the antiparallel state, an electron, say, spin up, might travel easily through the first layer. But in the second layer, where the magnetization is flipped, it suddenly scatters much more. The same happens for spin-down electrons, just in the opposite layers.
So in the anti-parallel state, both spin channels encounter high resistance somewhere.
Precisely. You're essentially removing a short-circuit path that exists when the layers are parallel. So anti-parallel alignment should mean higher overall resistance.
So they tested this on the Fecker-Fee samples.
They did. They carefully applied a magnetic field, used MOKIC and BLS to track the alignment parallel, then switching to anti-parallel as the field increased.
And measured the resistance.
And measured the resistance. The results were remarkable.
What did they see?
A dramatic increase in resistance precisely when the layers switched to the anti-parallel state.
How big an increase?
Compared to the standard anisotropic magnetoresistance, AMR, in a single iron film, which is tiny, like minus 0.13%.
Okay.
This new effect was significantly larger, big enough that it was eventually called Giant Magnetoresistance, GMR.
GMR, okay. Now, I read that some early experiments in Orsay, France saw like 80% changes. Grünberg's were smaller initially.
That's right. Albert Ferret's group in Orsay was working with multi-layers, many repeating layers, and saw those huge effects around the same time. Grünberg's initial double layers showed about 1.5%.
But even 1.5% was considered giant.
Absolutely. Compared to the existing AMR effect in metals, 1.5% was giant. The term stuck, and it applies to the underlying physics in both multi-layers and these simpler structures. And importantly, Grünberg's work with the AF coupling provided a clear mechanism and led directly to the patent application for hard drives.
Right. And achieving that anti-parallel state in a device, it doesn't have to be through AF coupling, does it?
That's a key point for applications. You can use the AF coupling, sure, but you can also build what are called spin valve systems. Yeah, you engineer the layers so they have different magnetic stiffness, different coercivities, or you pin one layer's magnetization using another material, an antiferromagnet, through something called exchange bias.
So you can switch one layer easily while the other stays fixed.
Exactly. The method varies, but the result is switching between parallel and anti-parallel states, and the underlying GMR physics is the same. Higher resistance when anti-parallel.
And the theory kept pace, the Camley-Barnes model.
It did. Developed right there in Jülich by Joseph Barnes and Bob Camley. It used Boltzmann's diffusion equation and provided a really solid theoretical framework that matched the experiments beautifully.
Amazing how theory and experiment went hand in hand. But the story didn't stop at GMR, did it? These insights led to CIMS.
Right. Current-induced magnetic switching. You could almost call it an inverse GMR effect.
Inverse GMR, how does that work?
Well, CIMS looks at what happens if you pass a strong electric current perpendicular through the layers, not just along them. You have a trilayer, one fixed magnetic layer, one free layer. And here's the kicker. If electrons flow from the fixed layer to the free layer, the spin angular momentum they carry actually exerts a torque on the free layer, switching its magnetization to be parallel to the fixed layer. Reverse the current flow, and the torque flips the free layer to be anti-parallel.
So the current itself switches the magnetic state.
Exactly. Predicted by Slonczewski and Berger, then seen experimentally, you're using electron spin to directly write magnetic information using current, a completely new way to manipulate magnetism.
That sounds incredibly important for future memory technologies, maybe.
Oh, absolutely. It's the basis for MRAM, magnetic random access memory.
Okay, let's bring this back home. What has all this meant for us, for everyday technology? You mentioned hard drives.
The impact has been absolutely monumental, especially in magnetic storage. Since GMR sensors hit hard drives around 1997, storage capacities just exploded, roughly 100 times bigger.
100 times. How did GMR enable that?
It's mainly because GMR sensors could be made much, much thinner than the older AMR sensors.
Why does thinner matter?
GMR is fundamentally an interface effect. Being thinner means they suffer less from demagnetizing effects, the sensor's own magnetism interfering with the signal. This allowed engineers to build incredibly tiny read heads.
And tiny heads mean?
You can read much narrower tracks on the hard drive platter, pack the data much, much denser. That's how we got from megabytes to gigabytes to terabytes in relatively small drives.
It really underpinned the digital revolution in many ways. But it's not just hard drives, right? GMR is used elsewhere.
Oh yeah, definitely. There are broadly two types of GMR sensors out there.
Okay.
First, you have those AF-coupled multi-layer sensors, like cobalt copper stacks. They give a big signal change, which is great, but they're unipolar. They can tell you the strength of a magnetic field, but not its direction, positive or negative.
So what are they good for?
Things like detecting rotation,
Mm-hmm.
gear teeth in ABS systems, in cars, for instance, or maybe sensing the presence or absence of a car in a smart parking lot. Simple on-off detection.
Got it. And the second type?
That's the spin valve type sensor. Yeah. They might have a smaller signal change overall. Their key advantage is they're bipolar. They can detect the polarity, the direction of the magnetic field.
Ah, which is crucial for
Magnetic recording read heads, obviously. You need to know if it's a north or south pole representing a 0 or 1.
Yeah.
And also things like electronic compasses in your phone or car.
Yeah.
They need to know north versus south.
Right. Makes sense.
And even the AF coupling itself, beyond GMR sensors, found uses. It's used in what are called synthetic antiferromagnets within the hard drive media, the platter itself, to help stabilize the stored magnetic bits.
So it's really permeated the whole technology.
It truly transformed how we store and access digital information. It's hard to overstate the impact.
It really is an amazing story. From, that lucky accident in Germany, seeing unidirectional spin waves, then the deliberate, careful engineering of these magnetic layers. It's just a perfect illustration of how fundamental physics drives technological revolutions. It's not just about bigger hard drives, is it? It's about really understanding the quantum world electron spin and how it influences our everyday lives in ways we often take for granted.
And it highlights how breakthroughs often come from this mix, right? Rigorous theory, innovative experiments, and yeah, a bit of luck or serendipity doesn't hurt either.
Definitely.
It's a reminder that all the tech we use, it has this deep, often complex, and sometimes surprising scientific backstory.
Indeed. So next time you save a huge file or just marvel at how much data fits on your phone, maybe give a little thought to Peter Grünberg, Albert Ferret, and the giant impact of magnetism. And here's a final thought to leave you with. We're always pushing for smaller, faster, more efficient data storage. So what other, maybe currently invisible quantum phenomena might be out there, waiting on the cusp, waiting for their own accidental discovery, or maybe some deliberate, clever engineering to become the next giant leap in technology?
That's the million-dollar question, isn't it? Or maybe $1 trillion now.
Maybe so. Thanks for diving deep with us today. We hope you feel thoroughly well-informed and maybe just a little bit inspired by the sheer wonder of scientific discovery.